In this lesson, we are talking about the different probability terminology that's out there, Venn diagrams, two-way tables, and how we can pull probabilities off of them. A probability distribution shows the probability of each outcome. A frequency table is often used to display that, and we have an example of that coming up. In a frequency table, there is usually something called relative frequency, and all that really is taking the frequency of a category and dividing by the total frequency. You've probably done this before when you found the probability of events. You took how often it happened and divided by the total number of times that it was looked at. Sometimes we turn that into percents. In this next example, it tells us a student conducted a probability experiment by tossing 3 coins one after another. Using the results below, what's the probability exactly 2 heads will occur in the next 3 tosses? So in order to do that, we need to look at the probability distribution and fill in those other relative frequencies. Finding relative frequencies, again, is the frequency of the category. So in this HHH category, we have it happened 5 times. And we want that out of the total frequency. And I've counted it out for you. If I add up all of these frequency numbers, it's 50. So to get our relative frequency for HHH, we take 50 and divide it, we take 5 and divide it by 50. That is 0.10. HHT, we'd take 7, divide by 50. HTT, 9 divided by 50. And so each time you try to find a relative frequency, you just take the frequency of that category and divide it by the total number. So you're going to go ahead and fill in the rest of the relative frequencies. You do not need to write the original fraction, although you could leave probability as that original fraction. You can do it as a fraction or a decimal. So whichever way you'd like to do it, with the fraction 6 out of 50, or actually divide 6 by 50. I don't care which one, fill in those last 5. All right, so we've got 6 out of 50 is 0.12. 2 out of 50 is 0.04. 9 out of 50 is 0.18. 10 out of 50 is 0.20. And again, 2 is 0.04. If I look at all of those relative frequencies and I add them up, the sum is 1. And that will always be the sum of your relative frequencies. Now back to the original question, it asks, using the results below, what's the probability exactly 2 heads will occur in the next 3 tosses? To do that off of our experimental results here, we look at which ones have exactly 2 heads. There's 2 H's here, 2 H's here, and 2 H's there. So to get the probability of exactly 2, and what I'm writing there is a probability notation. We put a P out in front, and make that P a little bit clearer. And then in parentheses, use probability of what you're trying to find. We can take straight from the relative frequencies and just add up the 0.14, the 0.12, and the 0.04. You could also add their frequencies and then divide by 50. Either way works. And I believe if we can do that math real quickly, go ahead and add those numbers. We've got a probability of 0.3. All right, the next thing we're going to look at is something called Venn diagrams, and you've seen these before. That's when you connect the circles. Sometimes people do them with squares. It's just 2 connecting items. Those items are connected because we have events that are made up of 2 or more events. So in this case, we've got A and B are the events. And if I want to find the union, which is all the events that are in at least one of the 2, and this is the symbol for union. It looks like a U, conveniently. So if I look at that Venn diagram, if I'm going to shade the union of A and B, I'm shading everything that is in A and everything that's in B. So there's our union. As you turn your page, the next one is saying A and B consists of all the events that are in both. This upside down looking U is a symbol for intersection. The intersection is the events that are in both. So it's got to be in A and in B. The only spot in this graph that's in both of them is this little football in the middle. One way I kind of remember which symbol is intersection and which symbol is union is I make this one kind of a weird word, and instead of intersection, I say intersection. So intersection, kind of just an easy way to remember what symbol goes with what. We use those because sometimes we have independent events and sometimes we have dependent events. Independent events means that the occurrence of the first event does not affect how the other event occurs. So here's an example. On school days, Janelle sometimes eats breakfast and sometimes does not. After studying probability for a few days, Janelle says, the events I eat breakfast and I am late for school are independent. Explain what this means in terms of the relationship between Janelle eating breakfast and her probability of being late for school. Remember, as you do this, you're thinking that the breakfast, the occurrence of the first event, does not affect how the other one occurs. So go ahead and write that out in language of somebody who hasn't taken any stats. All right, hopefully when you did that, you kind of thought through that the probability she's late for school is the same whether she eats breakfast or not. So it just doesn't matter. Oh, extra letter on that there. You could have said, doesn't matter if Janelle eats breakfast or not. She gets to school at whatever time. It doesn't, the breakfast doesn't affect her timing for the rest of the morning. Okay, then we have dependent events, and that's when the occurrence of the first one does affect how the other one occurs. Example, I didn't pay my electricity bill. My electricity was turned off by the company. Why are those dependent? Hopefully you looked at it as if you pay, the electricity doesn't get turned off. If you don't pay, it does. So payment affects service. So the one is dependent on the other. Service only happens if there's payment. Or electricity, if you want to say it that way, easier, if that makes sense, because service wasn't really in the sentence, but it's electricity service. It only stays on when the bill is paid. So they are dependent events. So look at this next one. It says choose a number tile from 12 tiles, then spin a spinner. Are those two things independent or dependent events? Hopefully you said independent. Because the spinner does not depend on the number tile at all. You take the number tile is completely separate from the spinner. The results on the spinner don't have any kind of reliance on the tile that gets picked. Okay. When we're dealing with different events, we have something called the addition rule. The addition rule is if I have these two independent events, I can potentially figure out what the probability is of their union. When I do that, I have that I would take the probability of all of A. So I've written it out in words and in symbols here. Probability of A or B, that's union. So or goes to union, is the probability of A plus the probability of B minus the probability of their intersection, A intersect B. I'm going to show you why this rule works. If you look at what the probability of A is, probability of A happening would be if I shaded in this entire circle. The probability of B would be if I shade in all of B. The intersection has both blue and red shading on it, which means that that football in the middle got added in there twice. It was added in when it was blue, it's added in when it's red, so we have to subtract one of them. So it's in the probability twice, so we subtract 1. And when we do that off of a chart like we're going to do on the next page, it almost becomes easier because you can just pull the numbers off the chart, but I'm going to show it to you with that addition rule just to make sure you recognize how it works. So on that last page, we've got the event, each student in a random sample of seniors at a local high school participated in a survey. These students were asked to indicate their gender and their eye color, and the following table summarizes the results. So we've got the 3 different eye colors that were given, brown, blue, and green, and then we've got the male and the female for the gender. We have totals on all of our rows and columns. So if you need to, you can kind of separate out your totals from the actual data. So we know right here there were 200 total students. And then we know how many said they were male and had brown eyes, or male and blue eyes, etc. So suppose that one of the seniors is randomly selected. What's the probability the selected student is male? So again, using that probability notation, we would put the P, and then I would just put male in the parenthesis. To get the probability of male, I would find out how many were male, which we can see right here is 110. And I would divide it by the total, which we said was 200. Again, probability can be given in fraction form or in decimal form. So when I took 110 divided by 200, I got 0.55. So in B, suppose one of these seniors is randomly selected. What's the probability that they have blue eyes? So that probability notation is P of blue. Go ahead and give me the probability that they have blue eyes. All right, hopefully you found the blue eyes is the 40. Oops, sorry, not 40. Blue eyes is 40 and 40, so that's my total of 80. But we're still out of the entire total of all the seniors. And 80 out of 200 is 0.40. All right, now we get another one. Suppose that one of these seniors is randomly selected. What's the probability that they are a male and has blue eyes? So remember, and is intersection. So I'm going to do that upside down U. So and intersection. So figure out the probability of male and blue. All right, looking at that one, male and blue, where male, this row, intersects blue is right here. It's this top 40. It is still out of my total of 200. So we've got 0.20. So that word and gives me intersection. All right, 3 more to go. Same chart on this page. I just did another page to make sure we can see what we're looking at. In D, it says, suppose that one of these seniors is randomly selected. What's the probability a selected student is male or has blue eyes? So again, with that probability notation, we want male or blue. Okay, this one, when you look at or, I'm actually going to replace that word or with the symbol. The symbol for or is union. And this one says show this probability using the addition rule. Because when you look at it, you have the male row that we know the total of. We have the blue column that we know the total of. But if you notice, I circled this number 2 times. So the probability of male, we would have had that number up in A, 110 out of 200. If I then add the value from B, which was 80 out of 200, that was the probability of blue, I need to subtract out that intersection because the male intersect the blue number got added in there 2 times. At that point, you end up with 150 out of 200, which is 0.75. Another way a lot of people like to do problems like this is instead of doing the whole addition rule, you can just literally look at what are all the numbers that are there for male and what are the numbers that are there for blue. So I could look at 50, 40, 20, and 40 and just add those 4 numbers up and then divide by the 200. So sometimes having the chart allows you to not have to use the addition rule. You can just kind of visually see what's going on. All right, the next one. Suppose that one of these seniors is randomly selected. What is the probability that the selected student has blue eyes given the student is male? Now that given word changes our situation a little bit. In all of the other ones, it was a randomly selected senior. It was out of everyone. But now we know that the person is male. It's not taken out of anyone anymore. So the probability notation for that changes a little bit. We want blue eyes. And then given is just this bar, given that they're male. What a given situation does means it's dependent now. It's no longer independent of each other. It's dependent on it being a male. So what that gives us is a new denominator. Instead of it being out of all 200, it's only going to be out of the total of males, which is 110. So now on that chart, you want where the males and the blue meet each other. What number is that? Hopefully you're saying 40, because that's this one, where male and blue intersected. When we divide that, you get 0.364. All right, knowing that, on the last one, we've got suppose that one of these seniors is randomly selected. What's the probability the randomly selected student is male, given they have blue eyes? So we're going to flip those 2 around. Male given blue. Go ahead and calculate that. Hopefully you now put the blue on the bottom. The total of blue is 80. Where they intersect is that same 40 that we talked about up above. Again, the 80 is coming from right there. And if we have 40 divided by 80, we know that that probability is 0.50. Now, one of the cool things that you can do to tell if something's independent or dependent is actually look at the two values that we've got. Up in A, we said the probability of male was 0.55. Because these two are not the same, knowing the blue eyes changed the probability, so they are not independent. Because remember, independent events, the first doesn't affect the second, or the second doesn't affect the first. And in this case, as soon as you know there's blue eyes, it changes the probability of it being a male, so they are not independent of each other.